Now, standing waves are not limited just to strings. We can create them with any type of wave. So you can make a standing wave in your bathtub with a water wave. One interesting problem we can do is figuring standing waves for sound waves. And we typically do this for a model of a musical instrument that we think of as just a straight pipe. It turns out if it's not straight, if it's curvy, then, well, it doesn't really change the situation much. All we really care about here is the length of the pipe and what happens at the two ends of the pipe, whether those are open to the air around them or sealed off. So we call these open pipe instruments or closed pipe instruments. The closed pipe one, we mean one side is open and one side is closed. I don't know if we really have anything where both sides are closed off. I don't think we'd do any instruments like that, but yeah, I'm not sure about that. I don't remember hearing about any like that anyway. Instead of thinking about the movement of the string, like we did with the last one, here we could think about the movement of the air particles, but it's probably easier to consider the pressure. So sometimes sound waves are called pressure waves or compression waves because they're rapid changes in pressure. And so if we think about the pressure, we know that the atmosphere, the air around the pipe, it's at a certain pressure, and there's a lot of air at that pressure. And if we get a certain spot in that area that ends up at a higher pressure, then well, there's lots of room for those air particles to spread out and very quickly get down to the pressure of the air surrounding them. They push outward until pressure equalizes. And if we get an area of lower pressure than the rest, then we'll have our air molecules have a net movement into that area until our pressure equalizes. So that's why you never walk through the room and suddenly find an area of the room where the pressure is really low and makes your ears pop, or where the pressure is really high and makes your ears pop. Those differences in pressure, they aren't sustained. So we can change pressure, but it doesn't last very long. And so for these open pipe instruments, we think of these open ends as areas where pressure doesn't change. Now, really, it changes there, just not very much and not for very long. So we'll think of these as being pressure nodes whenever we have an end that's open to the air. So all the way through here, at the very end of the pipe, I'll think of these as pressure nodes. And then in between, we can have the same kinds of variations we did before. Maybe I'll do that with the same color scheme we used a minute ago. So we can have one area where pressure changes a great deal, or we can have two areas where pressure changes a great deal inside there. Or we can have three areas, or any number really. Okay, something like this. So we'd have this blurring of the pressure. If we were watching a pressure meter at each location, we'd see this blurring of the pressure, just like we had blurring of the wave of the string. And so if we looked at each moment in time, we get really the same shapes that we had before. In fact, exactly the same shapes that we had before for the string. And then at the other moment in time, opposite that, we'll get these pictures. And so we have exactly the same conditions at the end. The string had to be held in place at the end. Here the pressure is being held in place at the end, which gives us exactly the same wavelengths and exactly the same frequencies. And so for an open pipe, we can say that the wavelength of the nth harmonic is going to equal 2L over N, just like it was for the string. And the frequency for the nth harmonic is going to equal NV over 2L, just like it was for the string as well. Now, if we go to the closed pipe, this is a little different situation. Here we have one side that's open and is going to have a pressure node at that side, but the other side is closed off. Now that's an area where there's no extra air right here that can get to the air that's inside because we have this seal in between. So these are areas where pressure changes the most, where we have antinodes for pressure. And so our first wave that fits in with these conditions is one that goes like this and just gets to a high point, or the opposite one would be going down like this and just getting to a low point there. And then here we might have one that goes up to a high point and then comes down to a low point. I didn't draw that very well to scale. Let me try that again. A little better. And then the opposite side is going to look something like this. Okay, or maybe we have an extra area where pressure is changing, and so we could have something like this, or opposite that, we would have something like that. Now these are definitely different shapes than what we saw before, and so our formulas are going to be different as well. Here, our wavelength, well, if this is a distance L, here to here, right now we've got from a node to a high point, or from an equilibrium spot to a low point, that's only a quarter of a wave fitting in that spot. So if I wanted the full wave, I'd have to have a distance of 4L. Here I've got, well, one whole up bump and then half of a down bump, or one full down bump and then half of an up bump. That's 3/4 of a wave. So if I needed a whole wave, I would need 4/3 of this distance L. And then last up here for this set, we've got one whole wave, a bump up, a bump down, and then a half of a bump up, so another quarter of a wave. So that one is 5/4 of a wave that fits into this space L. So to have just one wave, I would need a little less space. I would need 4/5 of that distance L. And so in general, I can say the wavelength for the nth harmonic is going to be 4L over n, but I'm going to specify that n for this one has to be equal to 1, 3, 5, etc. So we say we only have odd harmonics on these pipes. Now how we number them is sort of arbitrary. We could call this one the second harmonic and this one the third harmonic, because it's the second and third waves that fit with these boundary conditions. But calling this one the third harmonic, it has the advantage that the 3 appears in the equation, and it's going to appear in the frequency equation again. So there's some logic to the numbering system there. The frequency then, using the equation V equals F lambda, or F equals V over lambda. The frequency here for the first harmonic is going to be V over 4L. Here we'd have, 3V over 4L. This one would be 5V over 4L. And so we can see in general, the frequency for the nth harmonic is NV over 4L. And that's for a closed pipe. That's the frequencies and the wavelengths that will fit in that closed pipe situation.